If you're watching this, I am guessing you would like some practice on solving projectile motion problems if you are launched at an angle. So we're going to have an initial velocity that is going to be in both the x and y direction. Very similar to the horizontal only direction, only this time we are going to have to break our velocity into the x and y components first. Here's a sample problem. We have a baseball that is thrown at an angle of 25 degrees relative to the ground at a speed of 23.0 meters per second. The ball was caught 42.0 meters from the thrower. How long was it in the air and how high above the thrower did the ball travel? So since we have both a velocity and we have an angle relative to the ground, we're going to start by breaking our velocity into our component vectors. Remembering that the component in the x direction is VI cosine of theta, and our y direction is VI sine of theta. So let's do this first so that we can get all of our ducks in a row. VIY is then going to equal 23.0 meters per second sine of 25 degrees. You're going to type that in your calculator, and you should get a velocity in the y direction of 9.72 meters per second. In the x direction, we're going to have 23.0 meters per second times cosine of 25 degrees. And that's going to give us a horizontal velocity of 20.8 meters per second. Now that we have this information, we can add that to what we know in order to solve this problem. So let's go ahead and make a list of what we know. We just figured out that VI in the x direction was equal to 20.8 meters per second. We know our velocity in the y direction was equal to 9.72 meters per second. We also know that our delta x is equal to 42.0 meters. We also know that AX is 0, and we also know that acceleration in the y direction is negative 9.81 meters per second squared. The first thing always we want to find is going to be, can you remember? We need to know the time. If we don't have a time given to us, time is our key. Time is what we want to find. So let's look at our equations here and see if there's one where we can easily find time. I'm looking at my x direction, and I'm also considering that the main equation that I use is going to be the change in distance is the velocity with respect to time plus 1/2 a t squared. Now we can't use this equation as it is, so we are going to use this equation and only look at the x components. So that will give us delta x equals VIXT plus 1/2 AXT squared. As we've said before, AX is 0, so this part of the equation does go away. Now let's insert what we know. We know that delta X is 42.0 meters. VIX we calculated on the previous screen to be 20.8 meters per second times your time. We're going to solve by dividing both sides of the equation by 20.8 meters per second. That gives us a final time of 1.92 seconds. Remember, whether we're going in the X direction or the Y direction, time is the same for both. So now that we have the time in the X direction, we can go ahead and use that to find our maximum height. If we go back and reread the problem, it wants to know how high above the thrower did the ball travel. Well, let's draw a picture of that so we understand what it's asking for. So here's the ball. It's getting tossed at an angle. We know that angle above the ground is 25 degrees. It's going to go up in parabolic form, reach a maximum height, and then it's going to descend down to the person who catches it. So we are going to find the maximum height. Here's where the trick comes in. Parabolas are symmetrical. That means delta X, sorry about that, delta X on the half of it going up is the same as the delta X of it going down. Same thing with time. It takes half the time to go up and then half the time to go back down. The time we calculated on the last screen was the entire time of the ball's travel. In other words, from the thrower all the way to the catcher. It took that entire time. If we're calculating this specific height right here, it only takes the ball half of the trip to reach the maximum height. That is our key. Half the trip will reach us our maximum height. Half trip, which means it would be half of the distance or half of the time needed. So now let's gather up all the information that we know in order to go ahead and find the maximum height. So if you look here, the time for the entire trip we have already calculated to 1.92 seconds. We've also already calculated that the velocity in the y direction is 9.72 meters per second. And then, of course, we know that the acceleration in the y direction is always towards the ground or towards the earth at 9.81 meters per second. You might wonder why my VIY is positive in this case. And if we go back to the drawing, we're going to look at just the first half. So if you're starting down here and you're ending up here, your change in your y is going to be positive for this particular problem. Now the first thing we need to do is find half of the time is the time for your maximum y. And in order to do that, we're going to get 1.92 and divide that in half. That gives us a new time of 0.96 seconds. I'm going to cross out the old time so we don't accidentally use it. Now let's look at our equation, and we're going to use the y equation. So it's delta y equals 1 VIY delta t plus 1/2 AY delta t squared. Let's put in the information we know. We don't know delta y. We found that VIY from our components was 9.72 meters per second. We know the time to reach the maximum height is 0.96 seconds. Then we're going to add that to 1/2 acceleration due to gravity, which is negative towards the ground, 9.81 meters per second squared. And then we're going to multiply it by the time of half the trip squared. When you type each part in your calculator, you should find that the first part of the problem is 9.33 meters, and the second part of your problem is going to give you negative 4.52 meters. So now we just have to subtract, and we find out that our change in the y direction is going to be 4.81 meters. That is the distance between the thrower and the maximum height of the ball.